Okay. Just getting my screen set up. So today we're moving on to vertical and horizontal scaling. This is section 7.2 in your textbook. So for the first part, it'll be similar to the question from the last section. We're given the formula for a function g of x satisfying the following, and we have to determine, we have to write out that formula. So something to know is last time with shifting and scaling, we worked a lot with inputs versus outputs. The same thing with vertical and horizontal scaling. If you're, same thing as before, horizontal scaling, you're going to multiply the input by whatever factor. Well, actually, you're going to multiply the input by input by reciprocal of factor. Okay, and then we have vertical scaling, multiply input by factor. Okay, with horizontal scaling, if we flip over y-axis, we have negative times the input. And for vertical scaling, we flip over x-axis, we have negative times output. Sorry guys, this here should say output. Here for vertical scaling, we multiply the output by the factor. If these words don't make sense, it should make more sense once we get into some examples. If it still doesn't, either make an appointment with me or check out your textbook. This section does a really good job explaining this. Or you should be watching those lecture videos posted by the course coordinator. Maybe watch those again. But if this ends up not making sense, please seek help from me or the tutoring center or the tutoring specific for this course. All right, so this first one. The graph of g of a is the graph of f of x stretched vertically by a factor of 3. Okay, so since we're stretching vertically, we're going to multiply by the output. So we have g of x is equal to 3 times f of x. Okay. The graph for part B, the graph of g of x is the graph of f of x compressed vertically by a factor of 20. So now instead of stretching, we're compressing our graph, which means that now we have g of x, and since it's getting smaller, we have times 1 over 20 times f of x. Okay, so when you compress, it's getting smaller. So we give it a fraction, or we write it as a fraction. Part C, or actually, let's jump down. And if you guys don't mind trying to keep your worksheet in the right order, but I'm gonna just jump down to a different problem. Let's jump down to problem F next. The graph of g of x is the graph of f of x stretched horizontally. So now when we stretch horizontally, we have g of x is equal to f of x. So we have to multiply that input value, the x value, by our factor that we're stretching, but we're stretching horizontally by a factor of 7. And when we stretch horizontally, we multiply it by the reciprocal, 1 over 7 of x. Okay, kind of like when we're shifting, if we move right, we say that we say minus however many units we're moving right. And now in this case, we're going to take the reciprocal of whatever value we're stretching, or whatever factor we're stretching by. And then we're going to do g as well. So we have g of x is equal to, the graph of g of x is the graph of f of x compressed horizontally by a factor of 2. So we're compressing it, we're making it smaller, and it's happening horizontally, so we're going to multiply that input value. But since we're making it smaller, we're going to do the opposite. So we'll have 2 times x. Does that make sense?
So, just to clarify, the stretching and the stretching, compressed are complete opposite for vertical and horizontal?
Yes, the way that they have the same meaning when you look at a graph, right? Stretching, it's going to make it wider or taller. Compressing will make it thinner or shorter. So they have the same meaning when you look at it in a graph, but when we write these out as functions, we do the opposite in terms of whether we take the factor as is or we put it under 1. Does that make sense?
Yeah.
Great.
So usually when we're compressing horizontally, just don't do anything, just leave it the same.
When we're, yes, compressing horizontally, just multiply it by that factor. Same thing as when you're stretching vertically, you're just going to multiply it by that factor. But if you compress vertically, you divide by that factor. And if you stretch horizontally, you divide by the factor. So I think vertically makes sense, right? If I want to stretch something and make it bigger, I'm going to multiply it. If I want to compress something and make it smaller, I'm going to divide it. So if you remember vertical, then just tell yourself that horizontal is the opposite. Does that make sense or help at all?
Yep.
Good. Okay. Problem C. The graph of g of x is the graph of f of x stretched vertically by a factor of 3 and reflected over the x-axis. So this one's got a lot going on. So we first have that g of x, okay, is equal to, all right, it's f of x stretched vertically by a factor of 3 and reflected over the x-axis. So we're stretching vertically, so we're going to multiply this by 3. So we'll have 3 times f of x, and it's reflected over the x-axis. So we're going to multiply our output by -1. Does that one make sense to you guys? Any questions there? Okay. Now problem D. The graph of g of x is the graph of f of x shifted right 2 units and compressed vertically by a factor of 4. Okay, so now we're getting into kind of, there's an order of operations that really has to happen here. When we are shifting and scaling anything and writing new and old functions, we need to start by taking care of everything that interacts with the input first and then the output. So in general, you're going to deal with the input, or sorry, I'll say horizontal. First, you deal with the horizontal shift. Then you deal with the horizontal scale / if it flips over the y-axis. Then you go ahead and deal with the vertical scale / flip over x-axis. Then you deal with the vertical shift. So this is kind of the order of operations for this stuff. Okay, so going back to D, first we're shifting to the right 2 units. Okay, so we'll have f of, when we shift to the right, we're going to have x minus 2. And then we compress vertically by a factor of 4. And then, so we take this entire thing, f of x minus 2, and we multiply that by 1 over 4. Okay, any questions on that one, or the order of operations of how we have to go about when we have multiple things happening? Okay, moving on to E. The graph of g of x is the graph of f of x reflected over the y-axis, compressed vertically by a factor of 5, and shifted up 3 units. Okay, so we don't have a horizontal shift going on, so we'll move on to our horizontal scale / flip over y-axis. So we're going to have, I'm going to switch my color. G of x is equal to f of negative x. That's how we flip over the y-axis. And then we compress it vertically by a factor of 5. So we divide f of negative x by 1 over 5, and it's up 3 units, so we're just going to add 3. All right, any questions there? Okay, moving on to H then. The graph of g of x is the graph of f of x shifted to the right 2 units, stretched horizontally by a factor of 5, reflected over the y-axis, stretched vertically by a factor of 6, and shifted up 10 units. Okay, there's a lot there. Let's just go down our list of order of operations. So we'll have g of x is equal to, I'm going to give some space because it'll be f of something, because we might be multiplying by something here. So we are shifting to the right 2 units. So we'll have x, give some space again, x minus 2. And then that's being stretched horizontally by a factor of 5. So we're stretching this horizontally by a factor of 5. When we stretch horizontally, we multiply the input by the reciprocal of the factor. Okay. We're reflecting over the y-axis. So we're going to make this point, this 1 over 5 actually negative 1 over 5. Okay, so we got this done, we got this done, we got this done. Okay, now we have to stretch this vertically by a factor of 6. When we stretch vertically, we multiply by that factor. So we're going to go ahead and multiply this entire thing by 6. And then we shift up 10 units, so plus 10. And this is the final answer there. Any questions on that one? That one's pretty loaded. Okay. If there's no questions, we'll go ahead and move on. Problem 2, similar to the last section, identify the function being transformed and describe the transformations being applied to it. So problem A, f of x equals negative 2 times x minus 4 to the power of 3. This is what kind of function at its, what's the parent function's type? if I took away all my shifting and scaling happening. So if we took away this and that, that's our shifting and scaling that's going on. What type of function would x to the power 3 be?
Exponential.
Careful, exponential has the variable in the exponent. Here we have a variable raised to an exponent. What's this one?
Is it power?
Yeah, it's a power function. Oops. Power function. Okay, so now my shifting and scaling is highlighted. What am I doing, or what is happening to this this power function in the order that we have to have it in? So what's happening horizontally first? Is there a horizontal shift?
Yeah, it's going to the right 2 units.
Careful, it's going to the right 4 units. It's actually going to the left 4 units. It's going to the, I just copied this down wrong. This should be plus. It's being shifted to the left 4 units. And then what else is happening?
Is it reflected over the x-axis?
Good. And it's being stretched by vertically by a factor of 2. Any questions there?
So is the negative in front of the 2 how you know that it's reflected over the x-axis?
Yes, then when you multiply the output by a negative, so when the output here is being multiplied by a negative and not the x in the shift, we flip over the x-axis. When the input is being multiplied by a negative, we flip over the y-axis.
Okay, thank you.
All right, problem B. We have g of x is equal to the cube root of 2 times t minus 5 plus 9. Okay, so our transformations that are shifting and scaling is this 2, this negative 5, that plus 9. What type of function is the parent function?
Power function.
Power function, good. All right. Is there a horizontal shift happening? And if so, what is it?
Going to the right 5 units.
Good, shifted right 5 units. Okay, is there a horizontal scaling happening? And if so, what is it?
Is it being compressed by 2 units?
Yep. Well, by a factor of 2. By a factor of 2. Any questions on that one? That part could be a little tough. It's not. Are we scaling this function horizontally at all?
Shifting up 9 units.
We are shifting up 9 units. There's a step before that though. Well, that's the last thing that we do, but we don't have a, we're not vertically scaling this at all, right? This is all just being multiplied by 1, so we're not vertically scaling. But we are shifting up 9 units. Okay. Any questions there? Okay. Problem C, we have h of w equal to 1 over 4 times e to the power of negative 2w minus 7. All right, we have this 1/4, this negative 2, this negative 7. What type of function is the parent function?
Exponential.
Good. Okay, and do we, so now let's go in our order of operations. Do we have any horizontal shifting happening?
Honestly, I don't know how to tell with this one.
Good. Well, not good that you don't know how to tell, but good question. If we had horizontal shifting, this w would be in parentheses, and in the exponent, we'd have sum plus h. So we don't have one here. If we did, this is what the horizontal shift would look like.
So the negative 2 would be the horizontal scale and flip.
Good. Yep.
Okay.
So we do have a horizontal scale. We have horizontal. Is this being compressed or stretched?
Compressed.
Good. Horizontal compression by a factor 2.
It would be 4.
Horizontally, it's just, unless, yeah, I didn't write the problem down wrong. It's being compressed by a factor of 2 because that's what's being multiplied by our exponent. So horizontal compression with a factor 2, and we're flipping over which axis?
The y-axis.
Good. Okay, so we dealt with we don't have a horizontal stretch, but we have a we don't have a horizontal shift, but we have horizontal compression happening, and we are flip over the y-axis. Now we have to ask ourselves, do we have any vertical compression or stretching happening?
Yes.
All right, and what is it?
Would it be a stretch by a factor of 4?
So remember with vertical, if it's a fraction, we're compressing.
Oh, that's right.
So vertical compression by factor 4. We're not flipping over the x-axis because this 1/4 is positive. So lastly, do we have any vertical shifting? And if so, what way and at how many units?
Shifted down 7 units.
Good. Great. Any questions there? Okay. Next, we have y equals 2 to the power of 7 times x plus 1 minus 3. And our values that indicate shifting or scaling are this 7, this 1, and this negative 3. What type of function do we have initially? What- For a
Exponential.
parent function. Good, exponential. Okay. Are we shifting horizontally? That's our first question.
Yes.
Good. In which way and how many units? Anyone?
To the left by 1 unit.
Left, one unit. Good. Are we scaling horizontally at all? And if so, how
Yes.
so? How are we scaling?
Would it be a horizontal stretch of 7?
So careful. It's opposite the vertical. So since we have a whole number and not a fraction up here, it's a horizontal compression.
Oh, okay.
But it's, you're right, by factor of 7.
Can you explain why that would be compression again?
Yes. So if you look at C, we're multiplying our output, right? Our output is e to the power w. We multiply that by a fraction and we end up with vertical compression, which makes sense, right? If you multiply something by a fraction, it's going to get smaller. For vertical stretching, if you multiply it by a whole number, then you're going to get a stretching happening. With horizontal, since we're plugging everything into where the input goes, or we're adjusting the input value, we take the opposite of that. So we take the opposite. So when we multiply the input by a whole number, we're compressing. And then when we multiply the input by a fraction, we're stretching. So it's just opposite.
All right, thank you.
Okay. Lastly, do we have any shifting happening vertically?
Just down 3 units.
Good. All right, any questions on this page?
I was wondering, why do we not put that 2 as a vertical stretch? That first 2.
Because our parent function, the parent function here, that's a really good question, by the way. The parent function is 2 to the power x. And I know you're probably thinking, well, what if this 2 was originally 1 and it was multiplied by 2? But remember, we have this x attached to the 2. So if we had 1 to the power x, we can't just multiply 2 by it because it doesn't have the same exponent.
Okay, thank you.
Yep. So that was a really good question. I'm glad you asked that. All right. Any questions here? Any other questions, I should say?
Yeah, I have a question about
Mhm.
B.
Mhm.
Can you explain how it's compressed by a factor of 2 and
Yeah.
not
So
stretched?
yep. I should put the word horizontally in here. It's horizontally compressed by a factor 2 because we're multiplying the input value by a whole number. And when you do that, it causes compression. It's just opposite what you would think in terms of horizontal scaling.
Okay, thank you.
All right. Any other questions? Okay. Problem 3. Oh, I gave you guys a different one. I believe this is why I uploaded it late, because I was fixing this still. I got rid of this problem and I changed this to plus or minus 1, I forget. I think I just changed it to -1. Does that match the version you guys have?
Yes.
Okay, cool. All right, so use the graph of f of x to sketch the following transformations of f of x. So this first one here, what's happening here is we have a stretch, a vertical stretch by factor 2. You guys don't have to write that out unless you want it for your own notes. All I'm going to be looking for is your spot checking your graph. All right, so if we have a vertical stretch by a factor 2, our input values, our x values, what's on the x-axis versus the y-axis, stays the same. We're just going to multiply the output value, which is what's on the y-axis, by 2. So this first point here is 2, 2. I'm going to go ahead and multiply that y value 2 by 2. And so I end up with the point 2, 4. Similarly, we'll look at this point here, which is about 3. So it's the point 4, 3. I'm going to multiply the y value 3 by 2. And of course, this is too small. So I'll make my own 6 up here. 3 times 2 is 6. This goes up here. And so now we have the point 4, 6. Lastly, this last point here is about, I think it's like 1.5 more so. Yeah, 1.5. So 5 comma 1.5. We're going to multiply 1.5 by 2, which is about 3. So it'll stay here. And we'll have the 0.53. So our stretch, when we stretch it vertically by a factor of 2, that's what our new graph looks like. Any questions there? Okay, next. We have y equals f of 2x. So now we have a horizontal compression by factor 2. So now I'm going to take each of my x values and divide it by 2. Okay, so here we have the point 2, 2. That will become the point. I'll divide the x value by 2, which is 1, and the y value stays the same. So 1, 2. We have the point up here, 4, 3. 4 divided by 2 is 2. Our y value stays the same. So we have the point 2, 3. And then we have the point 5, 1.5. Our y value stays the same, but the x value 5, we divide by 2, which is 2.5. Which is about here. So 2.5 comma 1.5. And when we compress it horizontally by a factor of 2, that is what we end up with. Any questions there? All right, this next one, it's really important that we do things in the proper order. So first, we're going to take our input and we're going to shift left. Shift left 1 unit. Then we'll take our output and we'll divide it by 2. So we'll have our output is, so then we compress vertically by factor 2. And then lastly, we shift down 1 unit. Okay, so we're going to take each point. I'll start with this point here. And first, I'm going to shift it to the left 1 unit. So follow my dotted lines. Then it gets compressed vertically by a factor of 2. So I divide it by 2. Divide by 2, and I end up here. And then we shift down 1 unit. So the point 2, 2 becomes the point 1, 0. Did everyone follow that shifting and scaling with that point? Okay, next we have the point for 3. The first thing that we do is we shift left 1 unit, so follow my pen. So go all the way to where the 3 is, pretty much right here. Then we divide by 2, divide the y value by 2. So then we're left down at around 1.5. So about here. And then we subtract 1. So we're left at about 0.5. So now we have the point 3, 0.5. In this last one, in this last point, we again shift left once. So we're at our x value changes, divide our y value by 2. 1.5 divided by 2 is about 0.75. So it's just above here. And then subtract 1, so it's at negative 0.25. So this is the point 4, negative 0.25. So our last graph looks like that. Any questions with that shifting and scaling? Okay, moving on then. All right, use the table of values f of x shown below to write the table of values for each of the following transformations of f of x. So our first one, we'll have x, y, all right. So with this one, we're going to have to look at our inputs and our outputs separately. So anything that happens to the input, we'll figure out our new x values, and then anything that's happening to the output, we'll figure out our new y values. So we'll look at each point individually, each part of each point individually, really. So for our x values, we're shifting to the left 1 unit. So 0, the input 0 shifted to the left 1 unit is negative 1. 2 shifted to the left 1 unit is 1. 4 shifted to the left 1 unit is 3. 6 shifted to the left 1 unit is 5. Now for our output, we have f of x is negative 2. So that negative 2, that negative 2 is now going to be, so if we have negative 2, we're going to divide it by negative 2 first, then subtract 3. So we're left with 1 minus 3. Sorry, we're going to multiply it by negative 2. I'm doing the wrong operation. We'll multiply it by negative 2. So negative 2 times negative 2. So we'll have 4 minus 3, which equals 1. That's that new output. For the output 0.5, 1/2, we'll have 0.5. The first thing that we do is multiply it by -2, which gives us -1. And now we'll have -1 minus 3. Now we subtract that 3, which is -4. For 6, this output value of 6, we're going to multiply 6 by 2, which is 12. Sorry, by -2, which is -12. And then we'll have -12 minus 3, which is -15. So that value goes there. And lastly, we have -10 times -2, which is positive 20. Subtract 3, so 20 minus 3 equals 17. Any questions on that one? Okay, moving on to B then. We have X and Y. Okay, here our input is being compressed by -2. Since we're compressing by -2, our input we're going to divide by -2. So 0 divided by -2 is 0. 2 divided by -2 is -1. 4 divided by -2 is -2. And 6 divided by -2 is -3. Any questions there? Then for our Y value, it's we're going to multiply it by 3. So we'll have Y value times 3, then add 1. So when our Y value is -2, we have -2 times 3 is equal to 6. And 6 plus 1 is equal to 7. Oh, sorry, -6 plus 1 is equal to -5. So -5 goes here. Next, we have -2. Sorry, not -2, -0.5. Next, we have 0.5 times 3, which is equal to 1.5. And then we have 1.5 plus 1, which is equal to 2.5. So 2.5 goes there. Next, we have 6. So 6 times 3 is equal to 18. 18 plus 1 is equal to 19. And lastly, we have -10 times 3 equals -30. -30 plus 1 equals 29, -29. Okay. Any questions on that or anything that we've covered today?